When NASA's Curiosity rover drilled into a Martian rock, something went wrong. The drill bit locked tight against the surface, and the machine froze in place. This was not a simple mechanical jam. It was a test of whether a robot millions of miles away could think for itself when the human voice on Earth was 20 minutes too late. By the end of this story, you will understand why this failure was actually a masterclass in algorithmic autonomy and how it reshaped the way we build deep space systems. The incident began with a routine geological survey. The rover extended its robotic arm to penetrate a rock formation that had been selected for its scientific value. As the drill engaged, the torque sensors spiked. The rock was harder than the models predicted. The drill bit did not just spin, it seized. The arm was now physically attached to the rock, and the rover was at risk of tipping over or suffering catastrophic damage to its drivetrain if it tried to move while the arm was still locked. In a traditional engineering paradigm, the response would be immediate. An operator on Earth would see the telemetry, issue a stop command, and then manually calculate a recovery sequence. But the architecture of deep space communication makes this impossible. The round-trip light time between Earth and Mars is roughly 40 minutes. If the rover waited for a human to say, "Do this, then do that," the drill would remain stuck for hours, potentially leading to a mission-ending power loss or a structural failure. The system had to decide, wait for the human or act now. This is where the design philosophy of the Curiosity rover becomes critical. The onboard autonomy stack was not built to simply execute commands. It was built to interpret intent. The engineers had anticipated that the rover would encounter unexpected geological conditions. They had hard-coded a contingency state specifically for this scenario. When the drill encountered a resistance threshold that exceeded the safe operating limits, the rover did not wait for a command. It initiated a self-diagnosis protocol. Quick resource note: I keep a curated set of Amazon search links in the description for books, gear, and tools relevant to this channel's topics. Some are affiliate links, so I may earn a commission at no extra cost to you. Please consider supporting the channel by using those links if you find something useful. The rover recognized the anomaly as a rock attachment event. It isolated the drill subsystem and calculated the kinematic constraints of the arm. The system determined that the only way to free the drill was to retract the arm while simultaneously applying a specific oscillating torque to break the bond. This maneuver was high risk. If the calculation was wrong, the rover could tip over. But the algorithmic confidence was high enough to proceed. The rover executed a safe-fail heuristic. It traded physical risk for the latency penalty of communication. It acted because it had to, not because it was told to. Here is the thing that most engineers miss about this event. We often think of autonomy as a luxury feature that allows robots to do more work. In reality, autonomy is a survival mechanism for systems operating under extreme constraints. The Curiosity rover did not solve the problem by being smarter than the rock. It solved the problem by being more reliable than the communication link. The recovery strategy prioritized algorithmic autonomy over immediate ground truth verification. The rover executed the retraction maneuver based on telemetry confidence rather than waiting for Earth-based confirmation. This decision highlights a critical architectural trade-off in deep space systems. The choice to hard-code a contingency state into the onboard autonomy stack allowed the rover to self-diagnose the anomaly and execute a specific recovery sequence without human intervention. This proves that robustness in latency-constrained environments relies on pre-validated failure modes rather than real-time adaptability. The incident also demonstrates that what we call a mechanical failure is often a misclassification of environmental uncertainty. The rover's control algorithms successfully identified the unexpected mass change and dynamically adjusted torque limits and joint trajectories to free the arm. This showcases the superiority of closed-loop local control over open-loop command execution in high-stakes scenarios. The rover did not try to guess the solution. It used local sensory feedback to navigate the complex kinematic constraints of the stuck rock in a way that ground operators could not calculate in real time. This event underscores a career-relevant lesson in distributed systems design. The necessity of building graceful degradation protocols where the system can isolate a subsystem and continue operations or safely power down, rather than treating a single point of failure as a total mission abort. This pattern is essential for long-duration autonomous deployments. The solution required a shift from standard command and control engineering to intent-based autonomy. Engineers defined the desired outcome, which was to free the drill rather than the step-by-step mechanical actions. This allowed the rover's onboard AI to navigate the situation. The success of this recovery changed how we think about the relationship between the robot and the operator. The operator on Earth was no longer a pilot giving joystick inputs. They became a supervisor monitoring the health of the system. The rover was the pilot. This shift allows us to push the boundaries of exploration further. We can send robots to places where the communication delay is too great for direct control. We can trust them to handle the unexpected. The drill was eventually freed. The rover completed its scientific mission. But the real victory was not the rock sample. The real victory was the demonstration that a machine can make a life-or-death decision in a hostile environment without a human hand on the controls. It showed that we can build systems that are not just automated, but autonomous in the truest sense. They can perceive, decide, and act when the world does not go according to plan. This approach is now being applied to future missions. The next generation of rovers will have even more sophisticated autonomy stacks. They will be able to handle multiple simultaneous failures. They will be able to adapt their own control parameters based on the wear and tear of the hardware. But the core principle remains the same. We must design for the failure, not just the success. We must build systems that know what to do when the plan falls apart. The gap between theoretical autonomy and real-world failure recovery is where the real engineering happens. It is easy to write code that works in a simulation. It is much harder to write code that works when the rock is harder than expected and the human is 20 minutes away. The Curiosity rover taught us that the most important line of code is not the one that makes the robot move. It is the one that tells the robot what to do when it gets stuck. Thanks for watching all the way to the end. I am a one-person team working hard to make each video better than the last. Subscribe if you found value. It is the best way to show support. Drop a comment with your biggest takeaway. See you in the next video.